Welcome to the ftir.fun infrared learning series.
This episode, Ep02, Why do molecules eat light? The nature of molecular vibrations and infrared absorption. Then close with a checklist.
Next, adduction are chemical bonds like springs.
If you could magnify a molecule to a scale visible to the naked eye, you would discover a surprising fact. The atoms inside a molecule are not stationary but are constantly vibrating like two balls connected by a spring, moving back and forth around an equilibrium position. This is not just a simple analogy. In classical mechanics, the vibration of the spring follows Hooke's law, and the vibrational behavior of a chemical bond adds. Small displacements can indeed be described by the same mathematical model. Next, the spring ball model. Hooke's law. Imagine two atoms, masses m and m, connected by a chemical bond spring. When the atoms deviate from their equilibrium positions, the restoring force F produced by the bond is proportional to the displacement xie, where A is the force constant representing the stiffness of the chemical bond, and mx is the displacement from the B equilibrium bond length. The negative sign indicates that the force always points toward the equilibrium position, restoring. Next, i.e. quantized vibrational energy levels from classical to quantum. 2.1 Limitations of the classical model. Classical mechanics tells us that the energy of a spring oscillator is continuous. You can give it any amount of energy, and the amplitude will change accordingly. But real molecules are not like that. Next, beyond the harmonic oscillator, anharmonicity and the Morse potential. 3.1 Limitations of the harmonic oscillator model. Although the harmonic oscillator model is simple and elegant, it has a fatal flaw. The potential energy curve is a perfect parabola, meaning the molecule never dissociates. Next, types of molecular vibrations. More than just stretching and shrinking, the atomic molecules have only one vibrational mode, stretching along the bond axis. The polyatomic molecules are much more complex. For a molecule containing n atoms, the number of vibrational modes is IP known linear molecules. 3n-6 vibrational modes, linear molecules. 3n-5 vibrational modes. Next, colleague examples. Spic and Co. 5.1 Water molecule, 3 vibrational modes. Water is a non-linear molecule with 3n-6 equals 3 vibrational modes. Next, a rule for thought. Why is the vibrational frequency of the CH single bond 2900 cm higher than that of a C equals C double bond 1650 centimeters J8? Both has 3 vibrational modes. Why does the infrared spectrum often show only 2 distinct broad peaks? Finally, the drill actualists. Make sure you can recall each item. Core knowledge points. Key points. Spring ball model. Chemical bonds analogized to springs. Vibration frequency mu equals 1/2 pi mc. Mu Rn. Force constant K. Younger bond, larger K, higher frequency, triple double. Reduced mass I. Lighter atoms, smaller more higher frequency, bonds containing H have highest frequencies. Quantized energy levels. F equals m plus nu. Discrete levels. 0-point energy exists. Selection rule. Harmonic oscillator only allows delta V equals plus or minus 1. Fundamental absorption. Enharmonicity. Morse potential. Decreasing energy level spacing. Allows overtones. Fundamental frequencies slightly lower. Types of vibrations. Stretching, symmetric, antisymmetric, and bending. Scissoring, rocking, twisting, out of plane, bending. Number of vibrations. No linear molecules 3n-6. Linear molecules 3n-5. That covers the required sample for this episode. Practice with real spectra on ftir.fun and continue with the next lesson.